So hi everyone. We are here in the experimental cavern of the Atlas Detector at Cern. And we're here because this is the last day that the cavern will be open and accessible. After this, we will be closing the cavern to prepare for the restart of the LHC. So this is a very exciting day, and we're going to take advantage to give you a tour of the detector and show you what it looks like, explain to you how it works, and take your questions. So before we do that, we're going to introduce ourselves. So I am Elise Lubuliko. I'm a PhD student at Duke University, and I do research with the Atlas collaboration at Cern. And yeah, I work partially on data analysis and also a little bit on hardware for an upgrade of the detector.
Can you, just to check, can you hear us okay? Give us a, I see one thumbs up already, but give us a thumbs up if you can hear us okay. So we're just going to swap around. Can you come hold this a second? So, hi, my name is Dr. Clara Nellist. I am a particle physicist here on the Atlas experiment at Cern. And so I did my PhD working on the pixel detector itself. And now I mostly study top quarks, so these are the heaviest particles in the standard model. And also I work on machine learning, trying to search for new physics like dark matter. So Elise is our main host today. I'm going to mostly be behind the camera, collecting your questions. So every question that you have, please post it in the chat and we will get to that during the tour. Great.
All right, so before we start with the actual tour of the Atlas detector, I wanted to explain to you a little bit about what we do at Cern and what is the LHC. So here we are at Cern in Geneva, Switzerland, and Cern is the name of the laboratory that does particle physics research. And it's an international collaboration. There's institutes from all over the world who contribute, and there's a wide variety of research that's being done. So there's fundamental particle physics research, but there's also a wide variety of other things, nuclear physics, heavy ion collisions, also some experiments study clouds with so more environmental weather research. And so yes, within CERN there's a wide variety of research topics. The focus usually of CERN is the Large Hadron Collider, the LHC, and that is the 27-kilometer circumference particle accelerator that takes protons, which are small constituents of matter, and we accelerate them almost to the speed of light in two different directions around this 27-kilometer ring. And then at certain points, we make them to collide with each other. And when these high-energy protons collide, their energy is converted into mass of new particles. So you probably heard of the equation E equals mc squared. That's exactly what happens. So we're creating new particles in these collisions. And then we place these massive detectors around the collision points to measure what comes out. And so there are 4 collision points around the LHC. Atlas is one of them. It's one of the 2 general purpose detectors, so we're not really specialized, but we look for a little bit of everything. CMS is the other general purpose one that is across the ring from Atlas. And then there are 2 other ones, Lhc B, which focuses on one type of particle called a B quark. And then there's the Alice experiment that focuses on heavy ion collisions, because most of the time we collide protons, but sometimes we will collide also ions such as lead. So those are the 4 detectors that are around the LHC, but each detector also corresponds to one collaboration, so one group of scientists working together to build the detector and analyze the data. And it's important to have separate collaborations so that when a discovery is made, it can be verified or confirmed by another, for example. And so that's the big picture of Cern and the LHC. And so we're going to focus today on one of those detectors, so one small part of what is done at Cern in the LHC, which is ATLAS.
Great. So shall we give them a look?
Yeah.
Okay. So I'm going to take you off your perch here. Excellent. There we go. So where are we right now then?
So right now we're at the top level of the ATLAS experimental cavern. So the accelerator is located 100 meters underground, and so are the detectors. And so we've built this whole cavern to house the detector. And so ATLAS is the largest one. It's 45 meters long. So this what you see here is the length of the detector, and then its diameter, because it's a cylinder, so its height and its width is about 25 meters. So it's extremely large. It was not built in one piece. It was built in several pieces that were lowered one by one into the cavern and then assembled underground, a bit like a ship in a bottle. And this is because it was easier, just in terms of engineering, to lower the different pieces one by one.
Great. So yeah, we're above it right now, and then a little bit later in the tour we're going to go down.
Yes. So a little bit later we're going to go down a little bit closer to the center of the detector. So we'll be on the side of it, and we'll be able to see. Be level almost with the collisions that are happening at the center of it. And so we'll be able to see a little bit more of the different parts that it's made up of.
Excellent. So we've got a comment here already saying it's very impressive.
Yes, I agree. It's very impressive.
Yeah, so if you're watching, we're streaming simultaneously on YouTube and on TikTok, so you can come and watch us on either stream and post your questions there. So we're here to take your questions. So there's one question already to ask how people can get here for an excursion.
Sorry?
How people can get here for an excursion.
You mean to visit Cern? Yeah. So after today, the cavern itself will be closed for visits, as I said, because we'll be preparing for the restart of the accelerator. But you can always come to Cern, and there are some visits that are possible to do at the surface. So there's a exhibition in the visitor center that kind of walks you through what kind of research we do at Cern and the different types of research. You can also visit the synchro cyclotron, which was one of the first accelerators that was built at Cern. And so there are a lot of options, but to come here underground, you might have to wait for the next shutdown of the accelerator, which will be in a few years.
Great. And the next question was, how large are the magnets that we have?
Sorry?
How large are the magnets?
How large are the magnets? So it depends. There are multiple magnets in ATLAS. Maybe we'll see them better when we're a little bit lower, but they take up a big volume in the detector, and in terms of magnetic field, they vary between 2 and 4 Tesla. So yeah, they're very high magnetic fields. But we can talk about that a bit later. Yeah.
Yeah, and the toroids themselves, the whole length of the detector, right? So
right. Yes.
Huge magnets.
Yep.
So we have a thank you for your answer.
Great.
And there's another question asking, what day is the actual restart?
I don't know if it's officially decided yet. No, it's not decided yet, because they have to do a lot of different tests with the beams and the magnets and the cooling and all these things. So yeah, a few weeks to a few months, I think, is the plan.
Yeah. So along with doing all the upgrades and repairs that we have on the ATLAS detector, the accelerators as well have been getting repaired and upgraded, and so they're also finalizing that part of the preparations before we can restart. So there was another question that I just have to bring up. So there's a question, what is the energy scale?
Yeah, so the collision energy of the protons at the LHC is, well, for the previous one, it was 13 tera electron volts. So maybe if you're familiar with science, you might realize that that's a very, very high energy. It's the highest that's ever been achieved at a particle collider in the world. And actually, for the next run, when the LHC will restart, we will increase that a little bit to 13.6 tera electron volts.
Yeah,
so we're really pushing the boundary, the limit of what we can do in terms of energy. And the reason for that is because I said before that the energy of the colliding particles creates new particles. So the more energy we have, the more particles we can create. So that's really interesting for us.
Yeah, it'll be exciting when we go up to the next energy. But maybe also to add, even though this will be the highest energy collisions that humans have ever done, it's not even close to the highest energies that happen in nature. So in
That's
our
true.
atmosphere, there are higher energy collisions, but unfortunately we can't get our detector up there.
Exactly.
So that's why we have to do it. So there's a question here on TikTok as well asking how many women are working in physics. So they said they see so many women working here and it's great to see. So what's the sort of ratio, or how many women do we have here?
Yeah, I don't know the exact numbers. I think within physicists it's probably about 30%, something like that.
Yeah.
Within Cern in general, I think it's higher. But yeah, we're always working hard to be as inclusive as possible. But in general, I found there's a very good atmosphere and environment in this field of science.
Yeah, and also Cern itself is such an international environment. There's
Yes.
so many people from all over the world. It's a true mix of people coming together.
Exactly.
So there's a non-scientific question here. What does ATLAS stand for?
Oh, so ATLAS stands for A Large Toroidal Lhc Apparatus. So yeah, it's a bit difficult to remember the actual words that it stands for. It's I think it comes partially from in the mythology. Atlas was the one who was carrying the world on his shoulders, and so because Atlas is so big, I think that was one of the connections.
Yeah, great. So I'm just catching up with the questions. So somebody asked who is behind the camera. So my name is Clara. You can't see me right now because I'm trying not to drop our setup. But maybe I can very carefully just give you a wave. Maybe you can just hold that so I'm in shot. So hi, my name is Clara. I'm also a physicist here on Atlas, but Elise is our main tour guide today. So I'm holding the camera and making sure that I don't drop it on the detector before we close the cavern, mostly. So yeah, we'll have a couple more questions up here, and then maybe we can take a bit of a walk around and go and show another part of the cavern. Oh, so we've got some great questions. So there's one that just came up. So how crucial of a role will artificial intelligence play in Atlas experiment in the future? So machine learning, what are we using that for?
That's a very good question, and maybe you can add after, Clara, because you're kind of specialized in that. But one main way that we use machine learning, or otherwise known as artificial intelligence, is for analyzing our data. And so we get a lot of data from our collisions, and when we're looking for one particular process, one particular thing that's happening, we have to sift through a large amount of data. And so when we try to do that by hand, we will think about things that we can, like selections that we can apply, or some events that we can remove because for us they're not interesting. But machine learning can do a much better job at separating events that we think are more interesting or more likely to lead us to the result that we want, more than just our own guessing. And so that's one main way. I think there's also some research going on into applying machine learning also to select collisions in real time. So not just in data analysis afterwards, but as the data is coming in, we can't keep it all, so we have to make decisions very quickly on which collision events to keep and store for later analysis and which to just throw away. And machine learning can be very interesting for us in that regard.
Yeah, exactly. I think you summed that up really well. There's a lot of fantastic progress in machine learning in many different fields, and we're able to use that and improve on it for our own uses to select the data either live when we're trying to record it, or afterwards when we're trying to separate it from events that we're not particularly interested in.
Yeah, and in a similar way, the progress that we make with machine learning can be applicable also to other fields, and we can have an exchange that way, which is very nice.
Yeah, absolutely. So something unique, well, not completely unique, but something that we have a lot in our field is that we have such big data. And so we have huge amounts of data that we collect with our detector, and being able to sort through that is one of the specialities of being a particle physicist.
Yes, exactly.
Yeah. So we're getting some nice shout outs for some of our colleagues on here. So people who have been on a virtual visit before with Margarita and Marcus. And then also somebody wanted to say hi to Cooper, who's a PhD student from University of Massachusetts, I think that is. So hi to our colleagues.
Very nice. Hello.
So it's nice that people have had virtual tours before and seen some of the detector that way. So we have a question. What is the luminosity for run 3? How much data do we expect to get in run 3?
I believe it will be 300 femtobarns at the end of run 3. So that's approximately doubling the data that we have so far.
Yeah, absolutely. And so this is really useful then for the rare events that we're looking for, because we have to search through the data. So the more of them that we have, the better it will be.
Right, exactly, because we don't make discoveries based on just one event. We didn't discover the Higgs by just seeing one Higgs. We have to have a large number of them so that we can be sure of that conclusion and of that discovery.
Yeah. So one of the questions we just got is, what do physicists do when we're shut down? So what have we been doing for the last 3 years?
A lot of work. So first of all, there's a lot of work on the data analysis side, and that can be done at any time. So we've been analyzing the data from the previous run, and that's still ongoing right now. And then there's all the work that's been done on the detector. So a lot of parts needed to be upgraded or fixed or just tweaked a little bit to make sure that they were ready for the next run. Because some things that happen when the LHC runs for a long period of time is that we have radiation damage. So there's a lot of radiation that's being created by these accelerated particles, and that can damage some of the detector components. It can create leaks, for example. And so we needed to make sure that that was fixed, and that they would be able to sustain the next run. And then there were also upgrades. So, for example, there was a whole new part of the detector that was added during the shutdown called the new small wheel, and we probably won't see it today because it's a bit hidden, but it's one pretty big part of the detector that was constructed at the surface during the shutdown and then lowered into the cavern recently, and then it had to be incorporated into the rest of the detector, and so that was a really big effort for the Atlas collaboration.
Yeah, and so just to give some context, when you say small, I mean, we're going to see it better in a moment. It's behind this crane, unfortunately. But this is our big wheel, which is 25 meters in diameter. And so this is the large muon wheel. And the small muon wheel, the new one, is 10 meters in diameter. So a little under half the size, but still a pretty big section of the detector. So should we take a walk now?
Sure.
We can head down. So maybe just to give one last look above here. So just to let you know that this is the last virtual tour we have here in the cavern. Can we get a closer look at the detector? Yeah, of course we can. So we're going to go down now. Unfortunately, we have a crane here because this is the last day that we can be in the cavern, so everything's getting closed up, ready for restarting. But I'm just going to grab our bags, because anything we leave, we get in 3 years' time. And then we'll follow you. So there's a question here that I'm going to answer as we walk and try not to trip down the stairs. So we have a question which is, what is the probability that the standard model needs to be corrected or adjusted? So I think,
Yeah.
unless you want to take it, yeah, go ahead.
Yeah, so I can talk while we're going down.
Yeah. And maybe just as we go, I'm going to give them a peek here.
Oh, yeah.
Just. There we go. This is what we're about to go and see. Okay, on you go.
Yeah, so the question was about the Standard Model. So maybe for those who don't know, the Standard Model is the theory that we're basing all of our research on. And so it's a theory that tells us what types of elementary particles exist and how they interact. And so it basically tells us what happens when we have a collision, or what can happen when we have a collision. And so this theory, it works really well. We've been able to make measurements that agree with it very well. But there are still some open questions, some reasons why we think that it might be incomplete. Some of the reasons for that are dark matter. So from astrophysics observations, we know that there is a type of matter in the universe that is completely unknown to us, called dark matter. And that doesn't fit into our current model. So we would like to include it somehow. One other reason is the imbalance between matter and antimatter. Why there's more matter in the universe than antimatter. That is not really explained by our theory, but we know that it has to be true. And so there are other questions like that make us think that our theory of the Standard Model might not be complete. And so that's one big part of our research program, is to study some alternate theories or just some additions to our theory that could help explain these things.
Great, yeah. So we've got some quick questions that we can answer, and then we'll keep moving.
Yeah.
So the first one is, does CERN employ theoretical physicists?
Yes.
Yeah.
Yes, there are a lot of theoretical physicists who work at CERN. And it's very important because a lot of what we do experimentally in Atlas is to try to test some of these new theories. And so the theoretical physicists are the ones who come up with these new theories.
Yeah, great. And then the next one is, what are the pipes coming down into the ceiling?
Yeah, those are for ventilation. Because we are 100 meters underground, so we need ventilation, and also all the detector parts need very controlled environments. So that's what those are for.
Excellent. And then we had another quick question that I saw, which was, is this a wheel?
Yes, that is the big wheel.
And I suspect maybe this question is coming from the great internet debate we have at the moment, which is, are there more wheels or doors in the world? Which we're not going to answer right now.
Yes, that's a bit above our pay grade.
Yeah, there are lots of important people on the internet answering that question. But yeah, we have a wheel here. In fact, we have many wheels here in Atlas. So we keep walking to show you more of the detector. Let me grab some more questions.
Do we want to talk about?
Yeah, if you want to talk about it, great.
Yeah, so this is a nice spot because we get a really close-up view of one of the detector components. So what we see here is one of the muon detectors. So muons are a type of particle that is like an electron but heavier, so kind of a cousin of the electron. And muons are the only particles that are produced at the collision that arrive at the outer layers of our detector. So we need special detectors for them. And so these are tubes that will detect the muons. So they're aluminum tubes, and inside there's a gas and also a wire at the center. So when the muon passes through, it will ionize the gas, and it will create a signal in the wire. And then if we know that consecutive tubes received signals, we can reconstruct the path of the muon that came through. And so this way we can have a pretty accurate measurement of where the muons were, and we can then calculate their energy.
Great. Yeah, it's nice to be. We can get so close.
So close. Yeah.
And so just to say, if your question doesn't get answered, it's also because they move up the screen. So please feel free to post again. I'm trying to catch all the questions, but it's not always possible. But we'll try and answer as many as possible during the tour. So I saw one that was asking how much energy does it take to run the Large Hadron Collider and the experiments?
Oh, that's a good question. I never remember the number. Do you know, Clara?
So I think it's 600 gigawatt hours, if I remember that correctly, to run the LHC and all of the experiments. And essentially it's the equivalent of a small town.
Yes.
And that includes also then, it then also includes all of the offices, all of the people being here. And we have thousands of scientists that are working on these experiments. And so often we'll talk about the Atlas experiment, which we're talking about the detector here behind us. But we're running thousands of experiments on this detector, studying the data, and really, trying to understand all of the particles in the standard model and search for new ones. And so really it's thousands of experiments. And recently Atlas actually published its 1000th paper, I believe. I think that's right.
Sorry, published the?
We had a landmark in the number
of
papers.
Oh, the 1,000 papers, yeah, exactly.
Which was a great achievement. So that just shows how much science we could say, how much new information is coming from these experiments. And that's just Atlas, so there's also the other.
Right. Yeah. And also with the energy, it's actually one of the reasons why the LHC always stops, has a couple weeks shutdown around Christmas time, because it's the time of the year where there's the most energy consumption because of heating, because of holiday lights and things like that. And so having the LHC running and all the detectors running in addition to that would be a bit too much. So so that's why there's always a few weeks shutdown at that point. And usually physicists take advantage and upgrade or fix up the detector a bit during that time.
Yeah, excellent. And I see a couple different numbers here in the chat, so it depends whether you're talking just about the experiment, the LHC and the experiments, or the whole CERN site.
Yes.
But yeah, it's the equivalent of about a small town in electricity. Great. So I think we could keep walking.
Going?
Yeah, and if I miss any of your questions, please just repost them, and we'll try and answer as many as possible. So we have a comment here on TikTok saying, "Hi, Atlas." So
hello.
So we're taking you here on this tour to parts of the cavern that it's not possible to go to on an in-person visit. So we're taking you behind the scenes today, really get to show you everything with this experiment before we close this cavern up, and then we're going to start running the LHC again soon.
Yeah, so right now you have a much better view of the wheel that we were talking about earlier. And so maybe this is a good opportunity to explain a bit how the Atlas detector is constructed. So the principle is that it's constructed in layers. And so the particle collision happens at the center of this detector, which I said before is the shape of a cylinder. And so right next to the beam pipe, we have pixel detectors. And those are kind of like the pixels in a camera, where they're very small and we have a very good resolution, and we can measure where the particles come out of that collision. And then around that we also have silicon strips that are similar to the pixels, just slightly bigger. And so the inner detector is really focused on measuring trajectories. And then we have the calorimeters, and those are the next layer around, and their job is to measure the energy of the particles. So they will, the calorimeters will stop the incoming particles, force them to stop, and then measure the energy that they deposit in there. And so we use specific materials and gases to do that. And then, as I said before, the outer layer is the muon spectrometer, because the muons are the only particles that are not stopped in the calorimeters. And so we have all these muon detectors to specifically for the muons. And then if we combine the information from the different layers, we can reconstruct the whole path of a particle and also identify it. So for example, if we see something in the inner tracker and also in the muon system, then we can kind of figure out what happened in the middle and say that that was a muon. But if we see something in the inner detector that did not make it to the muon spectrometer, then it wasn't a muon. So in that way, we can identify the different types of particles that we have. Yeah, I forgot what I was going to say.
Did you mention neutrinos?
I did not mention neutrinos. That's what I was going to say. Thank you. So I mentioned that the muons are the only ones who make it to the outer layers. That's not completely true. There are also neutrinos. So neutrinos are another type of elementary particle that is not stopped in the calorimeter, but they are also not stopped or measured in the muon spectrometer. So actually, they are not measured at all. In ATLAS, we can't see the neutrinos because they're very difficult to detect, and they don't interact with any of the material that we have in ATLAS. They just pass straight through, and we can't see them. But we can kind of infer their presence through an imbalance in the collision products, because the products that come out of the collision, they fly out in all directions, and they should be balanced. But if we have a bunch of collision products in one direction and nothing in the other, then we can assume that whatever was in the other direction we missed. And so that could be due to neutrinos, but it could also be due to new particles that we don't know about, for example, dark matter. So that's definitely a possibility. And so when we analyze our data, we take that into account, and we calculate this, what we call missing energy, that can point us either to neutrinos or to new particles.
Great, so I'm going to go with another one of the quick questions. So we have a question here on TikTok saying, what does the cavern smell like?
Doesn't smell like anything in particular, in my opinion.
Yeah, I feel it just smells like any sort of like warehouse. Or
yeah, exactly.
It's just a little bit like work environment-y.
Right.
Yeah, can't really describe it.
Yeah, but like we said before, all the detectors have to have very controlled conditions. So the humidity, the temperature, everything is always the same and very controlled. So yeah, there's nothing too crazy going on.
Yeah. So then, I saw some great chats. Oh, somebody wanted to ask about the wheels spinning. So we sadly have to...
Yeah, they do not spin.
Yeah.
They don't move because they're very fragile, so we don't want to spin them.
Yeah, I mean, it would be cool to see, but unfortunately it would also make our measurements harder.
Yes.
So, and speaking of, a very keen-eyed viewer asked about all the cables that are in the gaps between the muon plates.
Yes.
How do we measure the particles that go through there?
That's a very good question. So there are actually plates behind those. So there are multiple layers, and the plates are kind of stacked and with a slight offset. And so we have some small gaps where we can't detect particles, but we try to minimize that. And so overall, we have a pretty good coverage, kind of 360 degrees around the collision point.
Yeah, and we have these multiple layers, as you were saying. That means that we get multiple points and we can create the track. So even if we have one small gap, then we can still recreate
we can
it.
still reconstruct the path of the particle even if we have a gap.
Yeah. So there's a question asking about sort of radiation down here. How long does it take for any residual radiation to dissipate from the cavern when the experiments are finished, making it safe for staff to enter during a shutdown?
Yeah. So yeah, you're right that the radiation does dissipate after the accelerator is stopped, and it's actually pretty quick, a few hours, I think.
Yeah.
But there's always tests that are done before letting anyone back in after a run to make sure that the radiation levels are under control. We do always have to wear a dosimeter when we're down here, so this measures the amount of radiation that we receive, just to make sure that it's below the safety levels. It always is. But we just want to be safe.
Yeah. So we have a nice question here asking, what advice, do you have any advice for students that want a future at Cern to build up certain skills they might need to be employed at Cern in the future?
That's a very good question. So in terms of skills, I mean, I guess it depends what type of research you want to do at Cern. If it's like data analysis, then programming is very important. If it's more technical or engineering, then anything in electronics will be helpful, like FPGA programming, things like that. But overall, just getting experience doing any type of research is always useful. And there are some programs, so there's the Cern Summer Student Program that is available for students in Europe, and that runs over several weeks in the summer, and you get paired up with a researcher at Cern, and you can work on a project for a summer. For students in the United States, there are various universities that do also summer research programs where you can work at Cern either, or with Cern either in the United States or coming here in Switzerland. So there are a lot of options to get started. And there's also the open data. So in Atlas, we release some of our data online, and it's called open data, and there are some really good tutorials to help you to get started, and you can just on your own kind of analyze some of that data and remake some of the discoveries that were made in the past, and that's a really nice way also to understand how we do data analysis in Atlas.
Yeah, and I think it is a really great place to start. And for example, if I was looking for students to come and join and they said that they'd use this data, and that just shows enthusiasm, and it's fun to do. So it's a really
exactly.
great program. So we have loads of questions. What does it sound like when it's running? How noisy is it in here when the LHC is operating? So we don't know directly, of course.
Yeah, we don't know exactly because we can't be here. The collision itself doesn't make any noise because it's actually in a vacuum. So the beam pipe where the protons are accelerated has to be a very good vacuum, because otherwise, if there were any air molecules or particles in the beam pipe, the protons would collide with those, and then they'd get off path. So it's very important to have a very good vacuum. So without air, there's no sound. So the collisions themselves don't make any noise. Any other noise would be due to the detectors. Probably, I'm guessing the cooling would make some noise.
So we can already hear now.
We can already hear a little bit, yeah, there's some background. But I don't think it would be particularly noisy.
Yeah, and even though we said that it's really high energy for each of the collisions, they're very, very tiny.
Right.
And so the energy is very concentrated, and so in terms of, it doesn't make any loud sounds. Maybe we want to keep walking and get a different view. So you want to...
Should we walk this way?
Yeah, we can go this way, go all the way around. So I'll look for another... You lead on and I'll look for more questions. So there's a great question here saying, does learning root increase chances of getting in Cern? And I think if people want to learn root, that's a great skill set to have for analyzing, doing analyses at Cern. So definitely wouldn't hurt. So there is a question asking if we can go inside to see the calorimeters or the trackers, but unfortunately we really can't, because today is the last day, as Elise was saying, that we can even be in the cavern, and then they're going to lock the doors, and from tomorrow and afterwards we're really preparing. I mean, we've been preparing for months, but really in the final stages of running the LHC and getting data with the detector. So maybe we can just explain, because we walked all the way down this corridor, and now, where are we now?
So this is actually the other end of the detector. So I said that it was a cylinder, so it's 45 meters long in this direction, and so where we were before was one of the ends of that cylinder, and now we're at the other end. And so the corridor that we walked was along the detector. And so you can basically see that on this side, it's the same thing, just symmetric. So we also have the Muon wheels, and maybe we weren't explicit about this. This blue tube here is where the beam pipe is, so that's where the protons arrive. There's a lot of shielding around it, but the actual beam pipe is only a few centimeters in diameter. And so the protons will arrive in that pipe and they will collide at the center of the detector a little bit further, yeah, in that direction.
Excellent. So, should we keep walking?
Sure.
There's a nice comment saying that somebody's really enjoying the tour, so thank you so much.
Oh, great.
So there's a question also about heat produced during the LHC run and after shutdown. So how do we control the temperature? I can tell you very quickly about the LHC itself.
Down or that way?
Yeah, either way. We could go down and have a look from another direction. Yeah, so the LHC, so we just saw the outside of the shielding of the accelerator. But there's, yeah, the dipole magnets that bend the particles around the beam have to be super cooled. So somebody else asked a question that we can answer here as well about asking that parts of the detector are colder than outer space, and that's also true with the dipole magnets. So the toroid magnets that we have in Atlas and the dipole magnets of the LHC are super cooled to 1.9 Kelvin, and so this is colder than outer space. And we use, superfluid helium, and we have to try and keep heat away from those parts because any increase in heat can increase the temperature of the magnets, and then they're no longer superconducting. And we do that through very specific, we have ways to carry the heat away. So in the beam pipe, there's a copper shielding that takes any of the heat away, and we have different cooling gases going through to cool the sections. But unfortunately we can't show you that here because the LHC is pretty much ready to go in our detector.
But yes, right now we're level with the beam pipe pretty much, and so this is where the protons arrive from. And you can, I always like showing that little
sure, yeah.
corridor. That one's fun.
So we can still hear you if you want to explain what's down this corridor. Do you want to explain what's down here, sorry? What are we looking at?
I actually don't know the details, but it looks like it's a lot of the cables and the fiber optics that are being brought to the racks for reading.
Yeah, so we have a lot of cables that need to come to the accelerators, to the detector, so that we can read out the data, so that we can run the detector.
Yep.
And here you can see, down here, one of the storage units for some of the cooling gases that we have here in Atlas. So I'm just, unfortunately we lost TikTok, but I can bring that back. So we're back on TikTok. Okay, we're only live on YouTube, but let's keep going.
Okay.
So should we walk down this way? I think we can go.
Yeah, or we could go down some more.
Yeah. I'm following you.
Okay.
So we'll just take one more look at the detector from this angle. Okay, let's keep going. So we have a question: which cooling gases are usually used for the detector? So I know that we have, so helium is one that we use a lot.
Right.
So superfluid helium is a specific state of helium. So it's liquid helium rather than in its gas form. And that's what cools down to 1.9 Kelvin, which is really, really cold. Mohammed has also added in the chat C3F8, we've got CO2. We also use liquid nitrogen for cooling. So different parts of the detector need different temperatures. And so we use different gases different gases for the different cooling. So again, now we're back on the other side, the original side we were on of the detector. And then we're going to go down to the ground floor, I think. Maybe we can quickly look at this diagram.
Oh, sure. Yeah, that's a good idea. So yeah, this is a kind of a schematic diagram of the detector. So these are the wheels that we've been talking about and what we've been seeing mostly. And then this is the beam pipe where I said the protons arrive. And so here we can actually see the inner parts that we can't see in person. And so like I said, these are the tracking detectors. They're really very close to the beam pipe. They only go out to about a meter out in radius. And then we have two types of calorimeters that come around. These are the green part here.
Yeah, and the orange part.
And the orange part. And then all around we have the muon spectrometer. And then we also have magnets. We mentioned magnets at the beginning. This is one of them. And then all the gray parts basically are magnets. And actually magnets are very important for us because they bend the trajectory of the particles. So when a charged particle is in a magnetic field, it will bend, and then the radius of curvature of that trajectory tells us about the momentum or how fast it's going. And so having these very powerful magnets, we're able to bend the particles that are coming out of the collision even though they're going extremely fast, and that way we can measure their energy. So without these magnets, we wouldn't be able to make almost any of our measurements. And so yeah, we have them. We have different types that create different fields in different parts of the detector based on what we need.
Yeah, so this is what's inside the detector that we're seeing today. So we also have a question about which direction does the beam run. So maybe we can point on the LHC here, and then we should probably keep going down. So we'll go to a lower floor.
Yeah, so actually the protons are going in both directions because they collide in the center. So they're around the LHC. There are two separate beam pipes, and there are two beams in opposite directions. And then when we get to one of the collision points, like here in Atlas, they're kind of brought together using magnets. And then they collide at the center of these detectors. So one beam will be coming in this direction, the other beam in the other direction, and they'll collide at the center.
Yeah, so we often talk about the Lhc beam pipe, but inside there are two pipes, one for each beam from the LHC, and then they, as you said, as they collide in the center of our detector.
Yeah, one interesting thing about that is we don't just collide one proton with one proton. We have bunches of protons, of billions of protons, that meets another bunch. And when that happens, actually only a few will really collide. In the last run, we had an average of about, I think, 30 that would collide at each time. Each time two bunches meet, only about 30 protons will collide. And that just shows you that there's so much empty space around those particles because they're so small. And so that's why we have a large number of protons in each bunch, so that we increase the probability of an actual collision happening.
Yeah. Right, I think we should maybe keep going.
Yep, go down.
Yeah, because unfortunately we're going to have to stop in a little bit. So as we said, this is the last virtual visit from the cavern, and then we will leave, and later today they will close it up. So yeah, if we missed any of your questions, please post them again. So we're trying to keep on top of all the questions, but sometimes they scroll up and we miss them. So here I think we can go under the LHC.
Oh, sure.
It's fun. Actually, this one's lower down than the other one. I regret this already. Okay, now we've done it. The other side has more of a gap. Okay.
We managed.
Yeah. So we can go down these stairs. So we have a comment that there are more doors than wheels so far that people have seen.
This way?
Yeah.
Yeah, now we're at the very bottom of the experimental cavern. So we started at the top, right above the detector, and now we're all the way under it. And so you see a different view, and maybe this gives you also an idea of the size of this detector. It's very massive.
Yeah, so we have a question saying this might be, so the question is, how do you get the protons to begin with to initialize the collisions?
Yeah, so it's actually a bottle of hydrogen, because hydrogen is just made up of a proton as the nucleus and an electron orbiting. And so then they take those hydrogen atoms and strip off the electrons, and then we're just left with the protons.
And then this goes in a chain of accelerators that we have.
Yeah, there's a few pre-accelerators before the LHC, because in order to get the protons to this high energy, now you can't do it all at once, so there are, I think, three pre-accelerators that are smaller loops, and they get bigger and bigger until we inject the protons into the Large Hadron Collider.
And how long does a run last?
A few hours. You probably know better than me, Clara, because you've worked in the control room, but sometimes you have to dump the beam because the conditions change a bit too much, but then it just restarts right away. So we try to take as much data as possible.
Yeah, so it's on average about 12 hours, 10 to 12 hours for a run. So actually what we can see, which is interesting, I didn't see this yesterday, the cavern is closed up there.
Oh, yeah.
So usually that shows us the surface. We can look all the way up to the surface above us, but that is closed, ready. So it really is the last day.
We can't lower anything more in the cavern.
Nope. Everything that's in is what's staying. So we have lots more questions. So one question is, why do we wear helmets?
Yeah, I mean the reason for that is that whenever we're in here, there's usually people working around, and there's always a risk that maybe something can fall from one of the upper levels, and so yeah, that's just as a safety precaution for that.
Yeah.
Just like any work site.
Yeah, and we also wear safety shoes.
Safety shoes, yeah.
Yeah, and as you mentioned earlier, we have our dosimeters. So we have lots more questions. Yeah, so some of them are getting answered in the chat, which is great. So there was one question asking if we have linear accelerators as well.
Sorry, I didn't hear
linear accelerators?
Yes. So yes, there are linear accelerators in various places, and they're used a lot. There are some pros and cons of linear versus circular accelerators. So linear accelerators are a bit easier because you don't have to bend the beam, and so you don't need magnets or as many magnets to control the path to be a circle. But the problem with linear accelerators is that you can't kind of recycle the beam. Once it went down once, it's lost. So yeah, there are, and it's also harder to get up a high enough energy in a linear collider compared to a circular one. But there are some plans to perhaps build a future high-energy linear collider, but those are still kind of in progress.
Yeah, so I'm just going through the questions again. So somebody's asking, can you please tell if we are physicists or engineers and what are our areas of research? So we did it at the beginning of the video, but we can do it again if you want.
Yeah, maybe I can also give a bit more details. So I'm a PhD student in physics, and I work partially on data analysis, and my analysis is testing one of the new theories that could complement the standard model, and that would predict the existence of a new particle that would decay in a certain way that could be very visible in the detector with 4 top quarks. And so, yeah, I've been working on an analysis that tries to see if we can reconstruct this new particle. And then parallel to that, I also work on data acquisition for the inner tracker that will be placed in the detector in the next shutdown in a few years. And so in 2029, we will enter what's called the high luminosity LHC phase. And so we will have a lot more collisions happening at once. And so the whole inner part of the Atlas detector that's used for tracking will be completely replaced. And so right now we're testing kind of chunks of that new detector. And so I work specifically on reading the data from those electronic chips and making sure that that readout is optimized and so forth.
Excellent. Yep, so
I mean, hold it?
Sure. I can't go too far though because I'm connected. So hi, hopefully, yeah. So my name is Clara. I am a physicist, also working on Atlas, hence the screen. Yeah, so my research now is mostly on the top quark. So doing studies of how it interacts with other particles, specifically looking at how the top and the Higgs interact together. When we produce 4 top quarks at once, this was a big achievement last year that we got this result out within Atlas. And then I'm also looking for new particles using machine learning techniques. So things like anomaly detection is my speciality. So using machine learning to search for things we didn't really expect would be there. So this is one way we can look for new physics. We can train these algorithms to look for, to understand things in the standard model, and then use the data to see if there's anything unexpected in there. So that's my focus at the moment. Yeah, and I used to work on the detector itself, on the pixel detector. So for my PhD, I was working on designing and testing new versions of the pixel detector. And I say helping because there's teams of us that do it. So it's really sort of a huge group effort to build these detectors. Great, so I think soon we're going to have to wrap up, so let's grab some more questions. I'm going to see if I can give like a nice, there we go, we can see the detector. So thank you so much, there's lots of nice comments saying people are enjoying the tour.
Oh, well, I'm glad they enjoyed it.
So yeah, and thanks, we've got people answering in the chat too, which is fantastic. Oh, and a really nice comment saying that we're cool, so I appreciate that. And we have someone who's about to start their Bachelor of Science with an honours majoring in physics, and their goal is to work at Cern, so hopefully
That's
one
great.
day, yeah.
Yeah, definitely.
So hopefully you come and join us on this side of the camera.
Yes.
Not, but you know what I mean, on this side of the tour when you come and work
It's
here.
a great place to work, yeah.
So let's find 1 or 2 last questions. I'm just going through, see if we've got some more stuff in. So there's a question asking if chemists can work at Cern.
Ken?
Chemists? Do we have any chemists here?
Not that I know of like pure chemistry.
Yeah.
But yeah, that's maybe my lack of knowledge. Do you know, Clara?
No, I don't think we have chemists here. And then another. Oh, there's a radio chemist in the chat. How many countries are involved in this experiment?
Yeah, so in Atlas, I think we have institutes from about 40 countries, but nationalities is closer to 100. So we really have people from all over the world. And yeah, people working in certain Atlas institutes in one country might come from a whole other country and have done their PhD in a third country. And so it's a very international collaboration, and also people have lived and worked in a lot of different places, so it really enriches the experience.
Yeah, and we're getting corrected in the chat, so Mohammed says, yes, we do have chemists.
Sorry?
Mohammed is saying we do have chemists.
Oh, okay.
So,
yep, I didn't know about that.
Too, yeah. So and there's somebody asking if there are Indonesians here. So yeah, we have colleagues from Indonesia.
Yes, I think so.
Yeah. Okay, so I think we should probably wrap up. That's been about an hour. I'm sorry that if we missed any of the questions. I was trying to go through to find the ones that we've missed, but there's so many wonderful comments.
And thank you for joining. It's been fun.
So I think so there's a question: what are the panels made of? Do we know what the panels?
What are the
panels? What are they made of?
You mean in the Muon
in the Muon
wheel?
Yeah.
What are they made of? I don't remember the material.
Maybe Mohammed can tell us in the chat. Okay, so I think we're going to have to wrap up because as you can see from up here, then the Cavern really is closing, and so Mohammed doesn't know either. Yeah, it's probably copper. I think there is copper in the panels, but it might be some kind of mix, so I'm not sure exactly. Yeah, and we have a question about if there are Pakistani scientists, and yes, we have people from Pakistan here at Cern. So yeah, thank you so much for joining us.
Yes, thank you. Hope you enjoyed it.
Yeah, all of the wonderful, wonderful questions. And yeah, if you want to come down here in person, then you'll have to come and visit us again in about 3 years.
Yep.
Otherwise, we do tours above ground too, so people can come and see the Cern site. And yeah, of course, I mean, we have all of our social media channels here on Atlas, so we're on TikTok, Facebook, Instagram, YouTube.
And our website, of course, has a lot of information as well.
Absolutely, yeah. So yeah, there'll be lots of new results coming out with our new data, and we're still analysing the data we've collected. There's still so much more to find out on the Atlas experiment. All of our colleagues that are working so hard as well to work out what our universe is made of on the smallest scales. Okay, so shall we say goodbye?
Bye.
So maybe I can wave. Great. Thanks so much for joining us, and hopefully see you on another live soon.